Okay. So welcome back. In this week, we're gonna start a new topic, recurrence neural network. Okay, so compared to our previous topic, convolutional neural network, to put it simple, we can basically categorize these two types of neural network based on the tasks that they are good at. The convolutional neural network, or CNN or ConvNets, it is a very useful network architecture to capture image information, to capture the information in 2D space, like the image is a 2D space, two-dimensional data structure, right? So how do we capture the features in the image effectively will determine how good a image classification model works, right? So the CNN model, basically it has multiple layers of convolutional layers and the polling layers. And in such a very deep model, the lower layers or the earlier layers, they tend to capture more lower level features, such as the edges, the color, the brightness, such shadow features. But the deeper features, which are at the later stage of the ConvNet architecture, they are more sensitive, or they can actually capture higher level features, like whether there's two eyes detected, whether there's hairs, ears, different parts on your face detected in those later layers, okay? So given a ConvNet, well, here I'm just giving a simple wrap up of the previous thing and adding maybe some new insights into the what a ConvNet can do. So if you take the intermediate representations, say you have 10 layers, 10 convolutional layers in the ConvNet model. Then if you take the output from the 10th layer, then that activations from the 10th layer is actually a very condensed representation for the input image, okay? And also the size of the features are significantly reduced, okay? So if you have 100 by 100 by 3 color image as your inputs, then you have basically 30,000 pixels as raw inputs. So that's your raw features. But if you take the condensed, the activation from the 10th layer out, it may be just a few hundred or a few thousand activations, which can be a very much shorter vector representation for the image. Okay, so you can directly take that representation out to represent the input image. And that vector, that intermediate vector or activation vectors actually summarize the input's image. Actually, it contains very rich information about what this information, what this input image is. Okay, so that is basically the overall architecture, structure, or functions of ConvNets. And what we're gonna talk about today, recurrent neural network. In theory, we can also think of it as a kind of a deep neural network. Okay, it is deep in a way that's it's not because we have multiple layers, okay, but it is because we have multiple time steps in our inputs, okay? So in terms of tasks that recursive neural network or RNN is good at, we usually will apply RNN to the cases where the inputs are sequential data. Say if I want to convert a audio wave Okay, so it comes in with a audio clips data, and I want to convert that audio wave into a sequence of words, right? Then we basically need to process the input audio wave sequentially. We start by analyzing the head, and then maybe 100 millisecond later, another 100 millisecond later into segments. And then we will need to process those segments of data in a way that the information can be understood in this sequence. Excuse me for a second. I think my daughter is coming to get the iPad. Be right back. Okay, so yeah. And also take another example as, say, if we want to understand the semantics of a sentence, right? I have said several words, say, this is a machine learning class. And then in order to have the computer understand what that sentence means, then we basically need to take each word as input, okay? But the sequence, the order of the words also contains very rich information. Like I put the word this before is, and I put the word machine before learning. Then these different ordering of words may have very different meanings, okay? So recurrent neural network has such a capacity to pick up those sequential information or the information in the orders in the input sequence. Okay, and because we can have multiple time steps in the input sequence, so that's why the model may look very deep from the dimension of time. Right? If you look at the time dimension, then it has multiple steps. Okay, so it is basically two different concepts of these two different types of deep models. Okay, so let's have some more introductory examples here. So RNN is good at, it is classified as a sequence models. So we can have various types of sequence data to be modeled. Say we have speech recognition task that the model will understand the input audio waves. And what this model does is to take the inputs and convert the input to some outputs in the form of discrete words here, right? So the different pitches are mapped to the different word segments, okay, or text data. And second task, sentiment analysis, right? It is often used in reviews data, like if we want to basically understand how well people rate something, like whether people like the movie, whether people like some merchants on Amazon, like we want to have the people's subjective reviews in addition to the scores they gave, right? So usually we can have the option that people rate you within a fixed scale, okay? But that is just that is a objective scores. But now we can have people to input their comments and then try to understand what the semantic is behind the comments. And a simple example is a like versus not like, right? Negative versus positive. So a sentiment analysis model basically takes input a sentence or short comments or even a short paragraph, and then condense all the information together and give an output in a real number and this y is a real number that indicates whether people like it or not, or its number basically measures the degrees to which people like the certain item. Okay, so in the case of movie, the output can be a predicted scores, like people's overall scores. Okay. Third example, machine translation. Okay, so this is a very cool technique that's nowadays we can use on our phone. Like we type in a sequence of words, or even we can speak to an app, and it can first apply the speech recognition to convert what you said to words, to a sentence, and then translate that sentence for you. So in this third task, it's a bit more, actually a bit more similar to the first case, right? Because the inputs is a sequence and the output is also a sequence. The Y, it contains multiple time steps, and it is not just a single output. It is not a number, not a single scalar value, okay? So basically, it's a sequence to sequence model, and we need to kind of map different the information, the elements at different time steps in the outputs to the inputs. We basically need to reconstruct the mapping relationships here. Okay, so this is a very big research area in natural language processing, machine translation. All right, and let me give another example, which is a very typical NLP task. Okay, it is nowadays a very basic task that's in order to understand the information in text. And one important step is that we need to recognize the named entity. Okay, so a named entity refers to like people's name, organization's name, city name, country names, like those proper nouns, like those entities, not regular words. Okay, not grammar words. So, like given the input sentence, okay, SDSU is recognized as an organization. Mission Valley recognized as a location, a place name. San Diego recognized as a city's name. Okay, so given to identify those entities, the task itself is useful in information extraction. Okay, so for example, if you want the search engine to understand your input to the input box, right? You type in some keywords you want to search, or maybe a sentence. Then the search engine, maybe what it does is to first analyze which entities it recognizes. Okay, it should recognize you are talking about some place, you're talking about some city, and then it can query the database in a more efficient way, because it stores different types of information. For example, the geography data sets, the organizational data sets, they are placed into different data, big tables, big database tables. So recognizing the named entity is a key step towards effective information extraction. Okay, and I'm gonna show the rest of the examples quickly. Like the sequential models cannot just not only apply to language data, but also to like input video. We have the video in nature is just a sequence of frames, right? And we can see the connection between frames, and the one frame leads to the second, and a short clip of multiple frames, they represent some actions, right? So now the computer vision based techniques, it basically can extract the key given a image of human body, the computer vision based models, like using the convolutional neural network models, can extract the body points, like the joints on upon your body pose, like the key points on your face, the hand gestures. Those can be easily extracted for each frame. Okay, and then how do we have more semantic representation of those key points, those key joints? Is that we need to apply some temporal clustering, right? We need to recognize that the relationship between different positions of your joints, they actually represent some motions, okay? So the RNN-based models can be applied in this case, that it recognized a continuous movements, a continuous action in a video, and then maybe given the inputs, video clip here, it can output some descriptive text showing that, okay, this is a walking person, this is a walking animal, and so on. Okay. And more broadly speaking, whenever the input is sequence or it has sequential information encoded, then RNN-based models are basically effective in decoding those sequential information. Okay, for example, the DNA sequences, the sequential information encoded in the DNA sequence may be related to some diseases or to some biological features that scientists are interested in. Then an RNN is able to model those mapping relationships. Anyway, having talked about so much about the examples, let's look at what a RNN consists of. What's the basic building elements of RNN? Okay, so let's first introduce some notations using an example from named entity recognition. It's a natural language processing task, and the input is a sequence of words, okay, or a sentence. Okay, so say in this input sentence, we have that bunch of words. Gandalf told Frodo that he must destroy the ring, okay? And because this is a named entity task, we want to recognize the person's name in this sentence, okay? So ideally, the perfect output should be like this. So the word Gandalf is a wizard's name, Frodo, the hobbit's name, right? We want the output to be 1 for these 2 words, okay? And all the other words, they are not person's name in this case, nor other entity's name, so the output should be 0, okay? So this is a very simplified version of named entity recognition, okay? We're just making binary predictions for each input's elements, okay? So now let's represent the input data with X and, more importantly, the superscripts in these brackets, in these sharp brackets, okay? So this 1 in the superscript means that this is the first time step, okay, in the inputs. And the 2 here indicates this is the second time step, and so on, okay? So basically, the last one is X9, okay, because we have 9 words in total. And we can use X superscript T to indicate the particular input elements at time step T. And we can also use capital T to indicate the length, okay? That is just some conventional definitions. So, and also for the output, because this is a named entity recognition task, the outputs also needs to be a sequence, because we want to tag each word in the input sequence. So the output is also can be recognized by Y superscript T, okay? And the length of X, length of Y, they equal, okay? Anyway, now, because when we train a model, say this is our first example, right? So this pair of X and Y, this is our first training example in our training sets. And we must have multiple training examples in order to train RNN, right? So we can represent the I's training example by putting I also into the superscript, but in the round brackets, okay? So now we have two superscripts in this case, but we need to distinguish them, right? The T is for time step, and I is just for the I's elements, okay? All right, and the tx of I in the round script, superscript is the length of the I's training example, and similarly to Y, okay? So now we can represent a pair, a data points by xi and yi, okay? And we can use a supervised learning algorithm, basically gradient descent, to learn the mapping between the x and y. And we need to keep this in mind that here the xi and the yi here, they are actually vectors in this case. Okay, the x is the input of words, and the y is also the output vector of tags. Okay, so that's some notations. You can see a lot of similarities from previous supervised learning examples, like image classification. Okay, but also there are some different places. Okay, so now let's further dive into the question of how do we represent a word. Okay, word is a special kind of data that is it's very different from image data. Like images are represented by pixels, and pixels we know is just numbers. We can simply take the pixel number out as a feature. Okay, but for word we need to first convert it into some sort of numbers, right? So the question, having this question in our mind, we can have several strategies to deal with it. And one way is that we can use the one-hot encoding, okay, to represent a word. And this is the typical practice of representing words with some easy techniques, okay? So the one-hot term actually is quite straightforward, okay? So first, we need to examine, given the training data sets, we need to examine the data sets by counting how many unique words are there in total in the training set. Okay, so given the data sets that maybe contains like hundreds of thousands of words or hundreds of thousands of tokens. Okay, so let me use tokens instead of words. Okay, then we need to count how many unique tokens or unique words, and that is the size of the vocabulary. Okay, so we know that most words, they are used repeatedly. They appear more than one time in the vocabulary. Then we just count the unique number of unique words in the training set. Okay, so for example, in this case, we have 10,000 words, unique words in the vocabulary. Then we can use the V to indicate this quantity 10K. That is our vocabulary size. Okay. And of course, we can ignore some rare words when we consider building a vocabulary, because the word, for example, the word that only appears one time or below a threshold, then we can consider it as some noise, because we don't want to the rows noise and the less informative words to cost us too much computational resource. Okay, so now given the vocabulary, each word has an index, which is its position in that vocabulary. Say if we rank the words according to their relative frequencies. Okay, so the article word A or N, they are more likely to be the most frequent word because they are used very often. So for example, in this case, A has the index 1, okay? And probably the word Frodo is at the position here. So the 2005 is the index for the word Frodo. And the Gandalf is the word here. The index is 4012. So anyway, each word can have its index in the vocabulary. Okay. So now what we can do is to represent the word Gandalf with a long vector that has 4,000, that has 10,000 elements in there in total. Okay. And there's only one non-zero element at the 4012 place in that long vector. Okay, so the total number of elements in that vector x1 is 10,000, but there's only one in the elements, and all the other 9,999 elements are 0. Okay, because we want to indicate that this vector represents the unique word Gandalf. Okay, so that is the so-called one-hot encoding for this word Gandalf. Okay, and then for the next word, toad, we also need to excuse me, represent it with a one-hot encoding, but this time the position of the 1 is in a different position because the index for toad is 7,677. So we will have that element to be 1 and all the other numbers to be 0. Okay. So next, all the other words, we can represent them with one-hot vectors. Okay, all these vectors, they have 10,000 elements in each. Okay, so that is a typical way of representing the inputs to a RNN model. And then let's now look at how the model is built to learn the mapping relationship between X and Y. Okay, so a typical regular neural network or standard neural network solution is that we can, right, given that 9 words, right, we can flatten them into like a very long vector, okay, and then connect the inputs with into some fully connected neural network with multiple layers, right, and then we try to like predict the try to generate some outputs, right? Maybe with a softmax layer that has 9 outputs. Okay, so a typical regular network is like this, but the shortcoming is also very salient because we need to change the architecture for different pairs of training data sets for different training data points because the X and Y's, they are of different lengths, right? And also the information are not passed from the previous time step to the next. The sequential information is not in excuse me, is not modeled, right? We just flatten the inputs and then scramble them into a regular network. And all the sequential information are gone, okay? And also the resulting model is huge, right? Because it's, if we use a fully connected layer, if we have 100 words in the inputs, then the hidden layers needs to be 100 times 10,000, which increases really big, really quick. Okay, so now we need to use the so-called recurrent neural network structure. Okay, so a recurrent structure is basically the repetition of the same computation, but applied to different time steps. Okay, and I mean by same operation, I mean the parameters at each time steps, they are shared. Okay, the W's, the B's, the weight matrix, the biases computed for the first time step, they remain the same parameters, and they will be used for the computation of the next time step and the next time step until we reach the end of the sequence. Okay, so in this example, the first time step, the first word x1 is feeding to the neural network, and some outputs prediction is computed, y hats, okay, is computed. And also some internal hidden representations is passed to the second time step, okay? So the activations A1, the activations at time step 1 is carried on to the second time step, okay? So when we compute the second time step, we need to use the activation from the previous time step and the current input, which is the second word, to compute the prediction for the second label, the second predicted label, y hat 2, okay? And then you can guess that the activations from the second word is also passed along to the third time step to compute the third computation, the third prediction, and so on until we reach the end of the sequence. Because in this case, we have the inputs capital Tx, capital Ty, they have the equivalence. So the activation from the previous time step is Tx minus 1 is also fed into the last computation. Okay, so this is the typical recurrence structure of the network. So one detail about the first time step, okay, is that we need to initialize the activations for the 0 time step, because when we have the first time step as the input, so we don't have any context information yet. So we'll just initialize some 0 vectors to indicate that, okay, this is our very beginning. We don't have any history. We don't have any historical information, historical data. Okay. So now let's look at the parameters. The WAX and WAA that are highlighted here and WYA are highlighted here are the parameters that will be used to compute the predictions, the outputs for each time step and the activations. Okay, we have 3 sets of parameters: WAX, WAA, and WYA. So the subscript here indicates what the outputs and what the input is for those parameters. Okay, so now all the parameters, they, as I said before, they are shared across shared across different time steps. Okay, the YA, let me use a different color. The YA, WYA, WAA, and WAX used here as the second time step, and those used as a third time step, they are actually the same parameters. Okay, they are shared parameters. They are not a new set of parameters. Okay, and only in this parameter sharing we can pass along the information in the old time steps to the information to the computation of the future time steps. Okay, if nothing is shared between different time steps, then the recurrent neural network doesn't capture the sequential information at all, right? Okay, so now let's look at how the activations are computed. Okay, so before that, in the future or as a simplified representation for the network or visualization, then we don't want to like lay out each time steps like into columns this way, but we will use a more compact visualization like this. We'll put a circle here. Okay, we have a rounded circle, rounded arrow that starts from itself and connecting back to itself, indicating that this activation is used to compute the next activation. Okay. All right. Or some people will indicate that this is like this in the different visualized way. Okay, so it's let the output connect back to the input end. Okay, but this is basically the same. They convey the same idea. Okay, so now if you look at how the computation of how the prediction for the third time step y hat 3 is computed. Actually, the previous input information, which is x1, x2, are also used in the computation of y hat 3. Okay, the previous information are not tossed away, but they are carried on. They are used in the prediction for the time step 3. Okay, so that is the magical place of magical where magic happens in recurrent neural network. Okay, but we can first, before we carry on, before we move on to the more details, we can think about whether it is enough or whether it is sufficient to have only the previous words used to predict the next word. For example, in the first example, he said Teddy Roosevelt was a great president. Okay, or the second sentence, he said teddy bears are on sale. Then when we read, say, if we block if we block the remaining parts of the of the remaining words, how do we know that when we talk about Teddy, it is a teddy bear or the president's name? Okay, so by judging from the previous word, he said, it will not help us to guess what the next Teddy refers to, right? So the context information in the future here is also helpful to recognize the word in the middle. Okay, so that said, the one-way recurrent neural network is not enough to fully extract the temporal information in the sentence, right? Because in natural language, in the way that human beings say something using a natural language, the context information is not just that's before the next word, but also the word that comes after, right? Because the word is determined not just by the history, but also by the future context, the left context and the right context. Okay, so that's some additional information here, and we now got to carry on to the computation details of each time step. Okay, so this is the typical forward propagation or forward pass in a neural network, in a recurrent neural network. Okay, so when we compute the output for the first time step, y hat 1, we need to use A0. Okay, A0, remember that we need to initialize to all zeros because we don't have any context information in the first time step. Okay, and A1 is something we need to compute at this step. Okay, A1, let's look at the equations carefully, is the WAA times A0 plus WAX times X1 plus some bias, okay? And then applied some activation functions, G1. So these activation functions can be a 10H or can be ReLU, okay? It's basically the regular choice of neural networks, okay? So you see that the activations from the previous time step is used, and the activation and the inputs at the current time step X1 is also used. and they are multiplied with different parameters, WAA and WAX. Okay, so now you see the meanings of the subscript, right? The subscript AA means that this parameter WAA is used to compute some new A from some old A. Okay, and this WAX means that this parameter computes some new A from the current X, right? So the subscripts, they have very salient meanings. And also the subscripts for WYA also is very explicit, right? It computes the current activation, the current outputs from the current activations, right? So if you look at the formula for Y hat 1, it uses WYA to times A1, okay? So the A1 is first computed here, okay? So A1 is used to compute the Y hats and plus some bias, okay? So the specialty about the second activation function is that we use some sigmoid or softmax outputs because we are using a named entity recognition task as an input, as an example, right? Because we want to make a prediction for each time step. We want to predict whether this is a person's name or not, okay? So this time it can be a sigmoid or a softmax layer, okay? But these activations can be changed, okay? If we don't want to make a prediction for each time step, then we can also simply use some other types of activations like ReLU, like 10H. These are all okay. Okay, so this activation choice, the choice for the activation function is very task dependent, task specific. Anyway, let's look at the second time step. Okay, the different place for the second time step, okay, is that we need to use the activations from the previous time step to compute the current activation. Okay, so in this case, I put the more general form of equations here. When we compute the activations for the time step t, we need to use the activation from the previous time step, t minus 1, times with the parameter WAA, and the current inputs at time step t, okay, times with a WAX and plus some bias. That is how we compute the activations for the current time step. And then the predictions for the current time step is to use AT. Use the AT we just computed here. Okay, so that means all this computation, this two-step computation, it occurs at each time step in the input sequence. All the parameters WAA, WAX, WYA, they are shared. They are not different across time steps, but they are exactly the same times, exactly the same parameters. Okay. So we can, what we can do is to simplify the notation a bit, because the purpose of WAA and WAX is to compute the current activation. So we can basically combine them together into one weight matrix, which is WA here, okay? And also the input is also combined into a joint vector, which is after we put the AT minus 1 along with the XT together when we append them into a long matrix, into a long vector. Okay, so that will make our representation much easier to write. Okay, so if we combine a activation vector, so another thing is that the activations are usually much smaller than the inputs vector, because if we represent the input vector as a one hot vector, then it is very large, right? It has 10,000 dimensions, because we have 10,000 unique words. We have the 10,000 vocabulary words in our vocabulary. And the activations for recurrent neural network is usually around the value around like 50, 100, 200, 300, okay, and maybe more. But it usually isn't that big, isn't like 10,000 that big, okay? So placing these two vectors together, we can have a weight matrix that is maybe 10,000 and 100 by 10, right? And our input is like this way, okay? So this is just some matrix tricks here. All right, so let's complete the forward propagation. So you will often see another notation that not use WX, WA, but people might use like three different matrices like V, W, and U to indicate the computations in the same that occurs in each time step. And this is just exactly the same process, but with different notations. If you combine W and the U together, which is also doable, okay? But this is just for your information that people may use different notations, okay? So now it is the key difference from recurrent neural network to the regular neural network. So the back propagation for a recurrent neural network is more complex than the regular shallow or deep neural network, or even more complex than a convolutional neural network, okay? Because the so-called convolutional neural network is just a shrinked feed-forward network, right? We just have a very small filter size rather than a fully connected layer. But in the back propagation for recurrent neural network, we need to carry out the so-called back propagation through time, which is a fancy name, but the nature of it is simply that we need to back propagate the gradients to previous time steps, because the previous time steps are used in the forward path to compute the current time step. Okay, so let's look at another example here. So after the prediction for y hat 1, the first time step is computed, and because this is a classification problem, we will have a prediction for each word, for each time step. Then we will compare the y hat 1 with the ground truth, say y1, right? Then we will have some loss computed, right? The loss describes, the L1 loss describes how correct y hat is compared to y1, right? How different or how far away y hat is from the ground truth. Then this loss will be used to compute some gradients for the parameters, right? So in the case of a binary classification, the loss function is in this form, right? Remember the loss function for a logistic regression, right? We have the y hat, the ground truth, and the ground truth, y minus ground truth, and the predictions within a log function, okay? So this is the typical loss to a logistic regression. So given the loss, we can compute the gradients for y hat 1, right? The gradients is backprop to the gradients for A1, right? Because A1 is used to compute y hat 1, right? Remember the forward pass formula, we use wy times A1 to compute y hats. Now we have the gradients for y hats, we can compute the gradients for the gradients for A1. So this is done through regular backprop, right? We can simply compute the gradients for y1 using the formula for regular back propagation algorithm. And also the gradients for the parameters, for the weight matrix, for the biases can also be computed using backprop. Okay, so that is the first time step. And also for DA, DWA and DBA, the same thing can be, the gradients can be computed because we have the forward pass formula available here. Okay, so we're not done yet, because A1 is not just in the computation for y hat 1, but also in the computation for A2 and y hat 2, right? So A2 is used to compute y hat 2, and y hat 2 will also generate some loss L2. L2 will be used to compute the gradients for y hat 2, and then the A2 will be computed. Okay, but since A1 is used in the computation of A2, so the gradients for A2 will backprop to A1 as well. Okay, so part of the gradients will backprop back to A1. And so is the next time step. The gradients from the loss of time step 3 will backprop back to A2 and all the way back to A1, as indicated by these red arrows. And even for the last time step, the computation of the y hat of the last time step will result in some gradients, and that gradients will backprop all the way back to the first activation. Okay, so in general, the gradients at later time step need to be will back propagate to the earlier time steps. Okay, so now let's look at using more formulas. Okay, but this slide may take more time to digest, but I will encourage you to spend more time to work on the paper to see whether the formulas are correct. Okay, so now we'll use an example at time step 4 to indicate how the loss computed at this step is back propagated through time. Okay, so that's the loss for for L4, right? For time step 4. And by applying the formula of the forward propagation, so we use sigma. Here the sigma is a sigmoid function, okay? And the outputs O4 is basically the linear combination parts for the output units, which is V times A times A4, okay? So this time we use the shorter notation, not WY, but V, but it's basically the same thing, okay? So the logistic regression, the rules tells us that the gradients for the DO, okay, so this O, you can imagine it as Z, okay? See, this O is just the Z, it's just a linear combination. So in the review of the previous lecture, we have softmax functions reviewed. We have the conclusion that the gradients for the linear part is the difference between the y hats and the ground truth, right? So that also applies to this case. So we can easily get DO, and DO will be used to compute the gradients for DV. So this formula is the regular backprop formula. And so far, only the information at time step 4 are used, okay? So that's for DV. But now, next, we can use the DO4 to compute DA4, okay? And DA4 is basically, is the transpose of VT times DO4. Oops. And then we can use so this is also applying the back propagation principles to these units, okay? And simply now we decompose the activations. Let's look at the forward pass, how the A4 is computed. There are two parts, right? We have A3 and the X4. So now we can compute the gradients for DZ and the DW4 and DU4, right? Because we have two parts of parameters, W and U here. So we have DU4 and the DW4 computed. Okay, so these, so far, the DZ4, okay, will be further used to compute the A3. So now we are traveling across time steps. the information in time step 4 will be used to compute the gradients for time step 3, okay, and the DZ3 as well. So that is where the red arrow indicates, okay. So the gradients for DA4 will be traveled back to the DA3, okay. So I'm gonna proceed quickly because a bunch of functions will be computed in the similar, a bunch of gradients will be computed in the same way, and until we reach the very beginning. And now I highlighted the gradients for the same parameters in same color, okay. We have 4 parts for the gradients of dW and du, okay. So the gradients for u consist of 2 time steps, which is du4, du3, du2, and du1. And the gradients for w also consist of 4 time steps because there are 4 time steps, including the current step before the current step. So we need to consider all these time steps when we update the parameters for w, okay? Because that is the full computation. So next, we're gonna use the summation of all these time steps to be the correct gradients we need to use to update du and dw, okay? So that is the back propagation through time in theory, okay? So this is a in theory computation. We can do this on paper, okay? And I want to finish the next point. In theory, we can do the back propagation all the way from the last time step to the very beginning time step. But in practice, we don't do that, okay? Because the gradients will get, you know, there's a gradients explosion or gradients, what's it called? Decreasing, demolishing, or I forgot what the word is, but the gradients can be very small or very big if we backprop the gradient through too many time steps, because it gets multiplied to too many matrices, okay? And that is also not timely efficient, vanishing gradient problem, that's correct. So we don't want the gradients to be vanished, and also we don't want to use additional costs, computational cost, to without gaining too much information, okay? Because in practice, we find that it's okay if we just backprop through time with a certain number of time steps, okay? We don't need to backprop all the way to the very beginning, okay? So in practice, we'll use some technique called truncated backprop through time. Like we let the backprop to stop when some certain maximum steps are reached, okay? So this code is just for demonstration. You don't need to read the code, but the truncate happens in the last for loop. So this for loop is basically defines how many backprop through time step we want to go, and it basically sets some upper limits, okay, with this backprop truncates parameter. That said, we don't want to go through all the way back to the very beginning. All right, and that's the forward pass and the backprop through time for recurrent neural network. So I think we can end today, and you will go back and spend some time on the forward pass and backward pass of recurrent neural network, and hopefully this will help you understand how recurrent neural network is different from regular neural networks. And next Thursday's lecture, we're gonna introduce different types of RNN architectures that are suitable for different types of tasks. And lastly, we're gonna cover the gated units. So probably in the next lecture, we're gonna cover the gated recurrent units, like long short-term memory units, like the gated recurrent units, and so on. So yeah, that's so much for the content, so much for the course today. And let me know if you have questions. All right, and have a good day, guys. I will meet you again on Thursday. Bye-bye. Thank you for coming.